My next topic will be about memory hierarchy and why do we need to have cache memory. Now, cache memory is not DRAM, it is static RAM, and it does not require any refreshing. And it has a much better access time. It's a cache memory which is inside the CPU. Now, why do we need it? Okay, why do we need it? I'll talk about this, the need for cache memory. Maybe I need to introduce it just, I still actually have 3 minutes today. So let me just here take a look at this slide. So over time, if you go back to the 1980s, 40 years ago, okay? If you go back to that time, there were no caches inside the CPU. Why? Because the CPU and the memory operate at the same speed. So the speed of the CPU is identical. So the performance of the CPU is identical to the performance of the main memory. So the CPU was slow and the memory was slow. So they were both slow. So there was no need actually for cache memory. Okay. So that was back in the 1980s. But with time, people have improved the speed of the processor. So the processor, the CPU became faster and faster at a very high rate. Now notice that this rate here, the performance, how it's growing exponentially, okay, over time. So notice that this actually line curve, how it's going up, that is the performance of the CPU. It was improving at a rate which is 55% per year until recently it started to slow down, okay? And this is why they switched to multi-cores. But in the old days, okay, the entire chip was a single CPU, and it was improving at a very high rate because the clock was improving. On the other hand, the memory was also improving, but not at the same speed. You can see that it was only improving 7% per year. That's the speed of the DRAM. So the DRAM was improving, but at a lower rate than the improvements in the speed and the performance of the CPU. So there was a gap, and this gap was increasing. There's a performance gap that was increasing over time. So if they want to run the CPU at the same speed of the DRAM, of the main memory, this is going to slow down the processor. So what was the solution? The solution was to introduce a cache memory inside the microprocessor. Okay, that was the solution. So even in 1995, Intel, initially it was just a single level cache, but by 1995, Intel has introduced even 2-level cache in the microprocessor. And today we have 3 levels of caches inside the microprocessor. So there is a cache hierarchy. Okay, that's actually the complex hierarchy. We need to understand caches. We need to understand the basics of caches. Okay? So the need for the cache memory is that because we have this performance gap between the processor and the memory. So for this reason, we have cache memory today. So as we have seen in the previous slide, there is a need for cache memory because we have this widening speed gap between the CPU and the main memory. If you look at the processor today, the operation inside the CPU can take less than 1 nanosecond. We are using gigahertz. Back in the 1980s, the clock was only in the megahertz. So the clock speed today is like 1000x faster than what it used to be back in the 1980s. So the speed today, the operation, the clock cycle is a fraction of a nanosecond. Whereas in the case of the main memory, it might require like 50 nanoseconds to access. So you can see there is actually this kind of speed gap. And each instruction involves at least 1 memory access. If you look at the program, every instruction has to be fetched from memory. So there is the address of the instruction. So the PC contains the address of the instruction, and the instruction has to be accessed, has to be fetched, has to be read from memory. And if this instruction was a load or a store, then the same instruction is going to access data, okay, in memory. So sometimes you can have a second memory access if the instruction was load and store. So you can see here a second memory access in the case of load and store instructions. And for this reason, the program is generating, okay, lots of memory addresses and accessing the memory frequently. If memory is slow, then this is going to slow down the operation of the CPU. So for this reason, we have cache memory today. So the cache memory is a small memory in size, but it's much faster than the DRAM, the main memory, and it can help to bridge the gap between the CPU and the memory. That's the meaning of the cache memory. So today I would like to go into the details, okay, of the cache memory. This is a typical memory hierarchy. So on top of this memory hierarchy, we have registers. So we have seen in the MIPS architecture, we have 32 registers, 32 general purpose, plus also we have another 32 which are used for floating point, but these are small in number. We don't really have that many registers inside the CPU. And the typical size is less than 1 kilobyte. Yani, for example, if you look at each register, for example, in the 32-bit architecture is only 4 bytes. If you look at the 64-bit architecture, it will be 8 bytes. Okay, that will be the size of one register. Then you say, how many registers do I have inside my architecture? You have 32. And even when you have 32 and you multiply it by 8 bytes, when you multiply 32 by 8, what do you get? 32 multiplied by 8, 8 bytes.
Got 250.
You get 256 bytes. And yes, this is even less than 1 kilobyte, right? You get less than 1 kilobyte. So for this reason, okay, this is not really enough. Yani you can only have few values stored inside registers. The access time is really fast. Yani to access a register and read or write a register and the register file, typically it takes actually a fraction of a nanosecond. Of course, technology is improving and these numbers can change here. I'm showing here less than half nanosecond, but it can be even much smaller than that, okay, to read or to write a register in the register file. Now, below, so this is the register file. Okay, so the register file appears on top of the memory hierarchy. Below that, we have the level 1 cache. Now, this level 1 cache, in fact, it can be 2 caches. We have one cache for instructions and we have another cache for data. Now, typically it is small, yani between, let us say, 8 to 64 kilobytes. So today, let us say CPUs tend to increase the size of the level 1 cache. So we might have 32 or 64 kilobytes. That will be for the level 1 cache. And the access time is still fast because the memory is small and it's made out of static RAM, not DRAM, a faster memory technology that does not require refreshing. I talked about this in my previous lecture. So the access time is still small. Yani it's around 1 nanosecond or even less than that. Okay, so that's the level 1 cache. Now, the level 1 cache is small. You cannot really store the entire program inside the level 1 cache. You can only store part of the program instructions and part of the data. You cannot really store all the data inside the level 1 cache. So for this reason, we have a level 2 cache. So if the instruction or the data is not found in the level 1 cache, then the processor will go, the CPU will go into the level 2 cache. And the level 2 cache is larger than the level 1 cache, maybe around like 1 megabytes. Okay, it can grow even up to 8 megabytes today. That will be the level 2 cache. The access time is longer, okay, than the level 1 cache. And basically the level 1 and the level 2 can both be integrated inside the same CPU. Now, if the data is not found inside the level 2 cache, today we even have a level 3 cache, but I'm not showing it here in this slide. But eventually, okay, even going through all of these cache memories, if the data is not to be found there, then we have to go all the way to the main memory. So the program is found inside the main memory. So that's if we have the data. So if we have we say if the data is not found, we say we have a cache miss. So a cache miss, it means that what we are looking for, the instructions or the data are not really found inside the cache. So in this case, we have to go to the main memory, and the main memory today can be large. And you can easily buy, let us say, a desktop or a laptop that has, let us say, 32 gigabytes of DRAM. It's DRAM technology. It's a different type of technology which is used for the main memory. But the access time becomes longer. It takes longer to access, maybe 40 to 50 nanoseconds, okay, to access, to read or to write the main memory. Yes, Sally, تفضل.
Doctor, can you please repeat the L1 cache and L2 cache?
I will go into the details of these. So
okay.
The level 1 and the level 2 caches are really small memories inside the CPU. So they are on chip, whereas the main memory is external. Okay, it's connected to the CPU through a memory bus. So there is a memory bus that connects the CPU to the main memory. So rather than fetching the instructions or loading and storing data from the main memory directly, the CPU can access its own internal caches, cache memories. So if the data, the instruction or the data is found inside the cache, there is no need to access the main memory. That's really the importance of the cache.
But Doctor,
okay.
There is
therefore,
a
it makes the speed of the CPU, it makes the CPU faster. However, if you have a cache miss, and the blocks are not really the instructions or the data is not really found inside the cache, then the CPU has to access the main memory. And this is, of course, slower. It will take, okay, longer to access the main memory. Okay. And there is an I/O bus between the main memory and the magnetic disk or the flash disk. In the past, people used magnetic disks until recently. The reason why magnetic disks actually were popular because for decades, they were invented for decades. However, they were replaced by solid state disks. Okay, they're called actually flash disk. It's a different technology. They use the semiconductor to store the files permanently. You don't need the power supply to preserve the files on the flash disk. The same thing, you don't need the power supply to preserve the files on the magnetic disk. The difference is of course, in the cost, in the speed. Magnetic disks actually can store more data. You can easily have like terabytes, okay, on a magnetic disk, whereas flash disks actually can store less data, and it becomes more expensive if you would like to store terabytes, okay, of data on a solid state drive. The difference also is in the speed. Now, magnetic disks are slower than the solid state disk. The magnetic disk might take between like 5 to 10 milliseconds, okay, to access, okay, let us say a file on a magnetic disk. Whereas the speed of the flash disk is much better. It takes less time. It's in microseconds. It's still a lot slower than the main memory, but faster than the magnetic disk. Okay, so this is basically the hierarchy. Okay, that's basically starting from the registers on top and then going all the way down to the storage, okay, to the magnetic disk or the flash disk. Right. So there is an important principle which is called locality of reference. It means that programs access only a small portion of their address space. You don't really have to have the entire program inside the CPU to start executing the program. You only need actually a small subset of the instructions and data is needed inside the CPU. So if we can place this subset of instructions inside the cache memories inside the CPU, then the CPU can run very fast. Okay. So the CPU does not really require all the instructions to be inside the caches. It only requires a subset of these instructions. The same thing for the data. And if you have, like, let us say, arrays, you don't really have to have large arrays, all of the data inside the CPU. You can actually transfer subset of the data, okay, from the main memory into the CPU at any point in time, and you can place them inside the cache, and the program can use this data while transferring other data. So we have this kind of principle, which is called locality of reference. And we have two different types of localities. We have locality in time, which is called temporal locality. It means locality in time. So this means that, let us see, if an item like an instruction is accessed then the program is going to re-access the same instruction again in the future. So there is this kind of tendency. For example, if you have a loop and you fetch an instruction inside the loop, then the loop is going to repeat for more iterations, and the same item, the same instruction is going to be re-accessed again in the future. Okay, so that's for example, this is known as temporal locality. On the other hand, we have spatial locality. It means that we have locality in space, okay, which means that there is a tendency to access contiguous instructions and data in memory. For example, if the program fetches an instruction at a given address, then there is a high chance that it's going to fetch the next instruction in memory, unless, of course, it jumps or it branches. But typically, the instructions are sequential in memory, and therefore we have this kind of sequential execution of the instructions. The same thing for arrays. You place the data next to each other in memory, they are contiguous, and therefore you traverse the arrays element by element. So you can actually store many elements or many instructions of the program, okay, inside, let us say, a block inside the cache. And therefore, when you transfer, you don't really transfer one instruction at a time, you transfer a block of instructions or a block of data from the main memory into the cache. Right, so what is cache memory? Cache memory is a small memory, but it is fast. That's the most important thing about the cache. Okay, so they keep it small to make it fast. So it is inside the CPU. You don't really see it. It's not really outside. It's this inside the CPU chip. That's the cache memory, and it uses SRAM memory technology, static RAM. Okay, static RAM is a faster memory technology than dynamic RAM. It does not require refreshing. Okay, so it does not really have the problems of the DRAM. So the idea is to reduce the average access time to memory. So rather than fetching everything cycled, so every time the program would like to fetch an instruction, rather than fetching it from the main memory, it can fetch it a lot faster from the cache memory. So the cache, it tries to take advantage or to exploit temporal locality and spatial locality. So it takes advantage of this. So it keeps the recently accessed instructions and data closer inside the CPU. That's the meaning of temporal locality. So therefore, let us say if the program fetches an instruction and it wants to refetch the same instruction again later in time, then in this case, the block exists inside the cache. So therefore, it can fetch it from the cache without the need to go to the main memory. The cache also takes advantage of spatial locality, which means is that it keeps contiguous instructions together inside blocks inside the cache. So the cache itself is made out of blocks, and therefore it keeps these contiguous instructions or contiguous data. If you have, for example, dealing with arrays, it will keep them together inside the blocks inside the cache. So rather than moving one instruction or one data item at a time, it tries to move the blocks consisting of multiple contiguous words, instructions, and data into the CPU caches. So therefore, okay, it's actually moving blocks. Okay, so basically the cache is made out of blocks, and therefore we transfer blocks of instructions and the blocks of data from the main memory into the cache. So the goal is to achieve speed, fast speed, because the cache provides fast access, okay, and also to balance the cost of the memory system. So this is the goal of the cache memory. So really, it's trying to make the CPU to run faster. Now we can introduce cache memories in the data path. This is the same data path that we have seen. This is our pipeline, simple pipeline CPU. We cannot really have an instruction memory and data memory because we cannot really fit everything, the entire program inside the instruction memory. We cannot really fit all the data inside the data memory. So these are really cache memories. So the cache memory is part of the CPU. It's integrated part of the data path inside the CPU. So here I have an instruction cache. I'm calling it iCache. It's a small memory. It will only contain a subset of the instructions of a given program. The program will be, the entire program can be in the main memory, but you can only have a subset of the instructions inside the iCache. And also you will have a subset of the data inside the data cache. So if you have large arrays, you don't need the entire array, all the data to exist. You might actually have many arrays, okay, or large data structures. So you don't really have to have all the data inside the data cache at the same time. You can only have blocks, okay, of the data inside the cache. Now, if the block is not found inside the cache, we say that we have a cache miss. So we can have a cache miss inside the iCache. So it's called actually an iCache miss here. So if there is an iCache miss, then the cache has to fetch, it has to transfer the block, the instruction block. So a block of instructions is transferred from the level 2 cache, if you have a level 2 cache, or all the way from the main memory. So we transfer here a block of instructions. So you can see here the direction of the arrow. So if a block of instructions here is being fetched all the way from the main memory into the instruction cache, that's when we have a cache miss. This is when the block is not found inside the instruction cache. The same thing for the data cache. If the block is not found inside data cache, then we say we have a cache miss. And therefore the block has to be transferred, but it will be a block of data, will be transferred all the way from the main memory into the data cache. For simplicity, I'm going to assume that there is no level 2 cache, but today in more advanced CPUs, we do have like a second level of cache and even a third level of cache. But this will make the hierarchy more complex. So for simplicity, I'm going to assume there is only one level of caches. So now the iCache and the data cache are both at level 1. So we call them level 1 caches. Okay. Now notice that in the case of the data block, it can be transferred in either direction because we can read and we can write data. So if the data is modified inside data cache, it has to be rewritten back to the main memory. I'll talk more about this. I'll come back to it more in details later. Okay. Fine. So now I would like to go inside the cache, and we need to understand the organization of the cache. Please feel free to interrupt me if you have any question, okay, at any time.
Yes, Doctor, I have a question here.
Tfaddal, yes.
The access time that you talked about in the previous slides, is it from a memory to memory, or it is from the CPU to the memory, or from the CPU to the cache?
Okay, let us say that, okay, if the block is found inside the cache, then the access will be very fast because the CPU can fetch instructions from the instruction cache, or it can do load and store in the data cache very fast without the need to access the main memory. You agree with this, Khalid?
Yes.
However, if there is a cache miss, whether the cache miss exists in the instruction cache or in the data cache, now this is going to cause the pipeline to stall because it cannot be fetched an instruction, or it cannot be load, let us say, data from the data cache. Then this is going to stall the pipeline, and the CPU is going to wait until the block is transferred from the main memory into the instruction cache or into the data cache. So here it will take longer, okay, to access because the block is not really found inside the cache. So we lose cycles if the block is not really found inside the cache. So whether we have a miss in the instruction cache or a miss in the data cache, then the CPU is going, so this is going to stall the pipeline, and therefore the CPU is going to wait, okay, for the blocks to be transferred from the main memory all the way to the instruction cache or data cache. And there is, of course, a cache controller that takes care of handling the cacheness. Okay.
Okay.
Right. Now, if you look today at any modern computer system, you will find there are actually many caches everywhere. Okay, so almost everything is like a cache. Okay, so for example, when you look at registers, you can think about registers as like a small cache, but for simple variables. But this is managed by the software because you can actually load and store. Okay, so you can load into registers, you can store registers. So therefore, you can place some variables that actually are really frequently used in the program. So this is all under the control of the programmer. So you can think about that, okay, about registers, like you are putting like a small cache for variables. Think about the first level cache as a cache on the second level cache. So if you have a cache hierarchy and the block is not found inside the first level cache, then the CPU will go first to the second level cache. Because if the block is found in the second level cache, it will be a lot faster to transfer the block from the L2 cache to the L1 cache. And think about the second level cache as a cache on the main memory. Or if you have a level 3, you can go to the level 3 cache before going to the main memory. But eventually we have to go to the main memory because everything will be in the main memory. And think about the main memory as a cache on the hard disk. That is interesting because the main memory does not really contain everything. It does not really contain all the files. Okay, it does not really contain all the programs. So these exist on the hard disk. Okay, I call it hard disk. It could be a solid state disk, and it does not really matter what type of technology we are using. But basically, the main memory does not really contain everything. So that's, you can think about the main memory this way. I did not talk about the branch target and the prediction buffer. I did not really talk about the branch prediction. I skipped this part, okay, in the case of the CPU. But there are also other types of caches inside the CPU, okay, that I did not really mention. So, so there are actually plenties of caches everywhere. Yes, you have a question?
Yes, Doctor. Why do we have levels? Why not one large cache?
Good question. Good question. Yes, good question, Amr. The reason is that if you increase the size of the cache, you are making it slower. So there is actually a relationship between the size of the memory and the speed. If you would like to have actually a fast access, you have to keep the cache memory small. So for this reason, the level 1 cache is kept small so that you can use the same clock cycle. You are using a clock cycle when you have like a 5 gigahertz CPU today. You are using a clock cycle which is 0.2 nanoseconds. Imagine you would like to access memory in 0.2 nanoseconds. Now, if you keep the cache small, it can be accessed that fast. But if you increase its size, okay, the time you start increasing its size, and when you have like megabytes or even larger caches, okay, then in this case, it's going to take longer to access. So for this reason, they keep the level 1 cache small to keep the most frequently accessed data inside the level 1 cache. And if there is a miss, they go to the level 2 cache, they make it bigger. And then if there is a miss, they go to a level 3 cache, they make it even bigger and bigger. And of course, main memory is much larger, but slower than these caches. Okay, does this answer your question?
Yes,
Ali?
thank you.
All right, Ali.
I have a question according to this, what you asked. If we want to increase the cache in the future, what's the better? We add a new level cache or we just increase the size of the cache?
Now, cache memory is occupying space. Yani the more levels, more complex it becomes. So they try to simplify. So the idea is to improve the technology itself. Yani by shrinking the size of these transistors, they can make the transistors faster and they occupy less area. So it's all a part of the technology itself, memory technology, the SRAM technology. So by improving the technology, the static RAM for the caches, they can make them actually faster. Increasing the more levels of caches is, although some people actually have proposed this, they have been doing this, is not really practical because you keep on adding more and more caches, occupying area on the CPU. Well, I mean, it's not going to help much. Eventually, at some point, it's not going to help much. So the most important cache is the level 1 cache. We can actually have a second level cache. And even today, they have a third level cache in multi-cores, which is shared by many cores. But beyond this, I don't think that actually there is a need to go to a level, although some people have even suggested to have a level 4 cache. It will never end, yani, okay? It is going to increase the cost more and more because once you start adding these caches, you are increasing the cost, okay?
Okay.
Right.